Hello, my name is Dr. Paul Nussbaum, and I'd like to talk to you about applications of integration, the Unit 3 homework that we have here in Math 220, Applied Calculus number 1. So really you should be reading Chapter 26 before starting the homework assignment. Not all the problems in the homework are going to be all figured out for you just by watching this lecture. We're providing an overview in this lecture, but the textbook really should be your primary source of information for those sections 1 through 6, as you can see here on the screen, of Chapter 26. So it's a fairly important chapter. We're only going to cover this one chapter in Unit 3 because of that. It's really important that you learn the applications of integration. Those are going to reappear in your careers in engineering technology again and again. Really, we're going to learn how to convert word problems into these integration formulas, and then how to apply integration in everyday engineering technology problems. So if you look at the next slide here, you can see that there's about 42 homework problems that I need you to work on for Unit 3. All of them are in Chapter 26. You can see that they're spread out amongst the sections. We do spend a little bit more time on Section 1 to make sure that you have a few examples under your belt. But as you can see, there's a wide variety of engineering technology examples to see how you'd use integration in the real world. So the key focus areas of the homework are the individual sections of Chapter 26. So I'm going to go through them one by one, giving either one example or a couple of examples if it's a little trickier. And definitely go back to the textbook as you go through the homework problems. So let's get started. Okay, so let's take a look at applications of the indefinite integral. So in this example, we imagine that we're launching a spacecraft straight up, vertically, and the acceleration a, which is measured in meters per second squared, of the spacecraft is equal to 6t squared. So the acceleration is 6 times the whatever time is squared. So we want to find the height of the spacecraft after 6 seconds. Now, they're using the letter S to represent the height of the spacecraft, and they're also using the letter S to represent seconds. So please don't be confused between the two of them. So find the height S of the spacecraft after 6 seconds. If the height S equals 12 meters when the time is at 0 seconds, so the spacecraft is starting off on a platform that's 12 meters high, and the velocity is 16 meters per second when the spacecraft is 2 seconds into its launch. So after 2 seconds, it's already going 16 meters per second. So why do we have these extra values, like the initial height of the spacecraft and the velocity of the spacecraft after 2 seconds? The reason is because when we have an indefinite integral, it's always got that mysterious constant added to it at the end. We'll need to know actual real-world values to turn that mysterious constant into a real-world number. Let's see how that's done. So first, we're going to use an equation that's in the textbook, equation 26.1, and that'll give us an expression for the velocity. So basically, the velocity is equal to the integral of the acceleration added up over the duration of time. So the velocity is equal to that little squiggly symbol integral of 6t squared dt. We always put the dt there because it's respect to time. So the indefinite integral of 6t squared is equal to 2 times t cubed plus a mysterious constant, we'll call it c1. So how are we going to find c1? Well, they did tell us that the velocity at 2 seconds into the launch was 16 meters per second. So let's plug those numbers in. I'm going to plug in a 16. This is the second row of equations here. 16 equals 2 times 2 seconds cubed plus this mysterious c1. So if 2 seconds cubed is 8 times 2 is 16, so really c1 must be 0. In this case, there is no need to add any constant. So the formula is simply velocity equals 2t cubed, t to the third power. So now we want to find how far is the spacecraft traveled. So we know that the distance is the integral of the velocity, sort of the integral of the integral, if you will. The velocity was the integral of the acceleration, and the distance in height, once again using that letter S for height, is the integral of the velocity. So the velocity is 2t cubed, and when we take its indefinite integral, we see that it's 1/2 t to the fourth power plus a mysterious constant, constant 2. How do we figure out what that mysterious constant is, that missing constant? We plug in the values for, we know that the spacecraft at time equals 0 is going to be 12 meters off the ground. The launching pad is 12 meters tall. So we'll plug in that 12 equals, and then 1/2 t to the fourth. Now in this case, t is 0 seconds. So we find that C2 must be the number 12. So the distance off of the ground is equal to 1/2 t to the fourth plus 12. So if I want to know how far is the spacecraft after 6 seconds, I just plug in the number 6 for the amount of seconds, and I get 1/2 6 to the fourth power plus 12. It's going to be 660 meters off the ground. So if we want to find areas by integration, we might want to find areas not just underneath a curve, but we might want to find, for example, the area between two curves. So I've got an area that I want to measure, this light blue area in the picture, and it's bounded on the top by a straight line, which is the formula y equals x plus 2, and it's bounded on the bottom by a parabola, which has a formula y equals x squared. Now at the bottom of the screen you can see how we find where those two curves intersect. You can see that they intersect at x equals -1, and they also intersect at x equals plus 2. So how did we figure that out? We simply set the two formulas equal to each other, x squared equals x plus 2, and then we solved for x, and we got that x is either a -1 or a +2. To find the y, we just plugged those x's back into either one of the original equations, and that's how we found the 2 points of intersection, parentheses -1, (1), and parentheses, that's the lower left dot on the curves, and then parentheses 2, 4, and parentheses, that's the upper right-hand dot where the two intersect. So that's what, if you wanted to find the 2 points of intersection, you need to know that because you need to know where your shape starts and ends. So it kind of starts to the left at -1 and ends to the right at 2. So we can go ahead and add up all these super thin rectangles, as we learned already. We're going to choose vertical rectangles because that way they'll be bounded all the time by those same two functions. If I chose horizontal elements, I'd have to do two formulas, one where the straight line is involved and the other one where it's just the parabola. So I'll just do it vertically. It seems easier. So how do we solve that? The area of that super thin rectangle is whatever the top line is, the straight line, the y value of that, minus the y value of the bottom curve, which is that parabola, and that's the height of the rectangle, and the width of the rectangle is super, super thin, dx, right? It's that infinitely thin dx. That's what we're doing the integral. And I want to take all of those slices from -1 all the way to 2, as x goes from -1 to 2. So that's really how we're going to find the area between these two. So the formula for the line is y equals x plus 2, so I'll put that in there. And the formula for the parabola is y equals x squared. So I'll take the formula of the line minus the formula of the parabola. That's how I get in the second row there. I get x plus 2 minus x squared all times dx. After I take their integral, I find that I have x squared over 2 plus 2x minus x cubed over 3. And I want to evaluate it at 2 points, the 2 and then the minus 1, subtracting 1 from the other. If I plug that x squared over 2 plus 2x minus x cubed over 3, if I plug a 2 into that, I get 2 plus 4 minus 8 thirds, minus plugging a negative 1 into that. I get a 1/2, a minus 2, and a plus 1/3. Going ahead and doing the math, I find out that the total area in light blue is 9/2, or 4.5 units squared. So that's basically how you can find the area by integration. Now, we don't only have to find area, we could find the volume of something. So let's say we've got a tweeter cone that's, you can see them on many speakers. And the size of the cone where we're going to put the speaker will change the frequency response of that speaker. So we often need to find the volume of these kind of cone-shaped objects. And in this case, we're going to make that solid, this cone-shaped thing, by taking the function y equals x squared, and we're going to rotate it. We're going to spin it around the x-axis. And from left to right, it's going to go from x equals 0 to all the way to x equals 2. So that's pretty much, we're going to spin that curve around and end up making a cone. And we want to find the total volume of that cone, the amount of air that's contained in cubic units of that cone. So from the figure, we can see that the radius of any individual teeny thin, super thin disk would be y, right? The value y is the radius of any of those little disks. And those super thin disks, I'm going to add them up to find the total volume. Now, instead of adding a rectangle, I'm actually adding an entire volume disk, if you will, a thickness, like a little frisbee, but they keep getting bigger and bigger as you get from left to right on the cone. So the volume of that disk is equal to pi r squared times the height of the disk, right? So pi, I don't need to integrate that. I can pull that out of the integral because it's a constant. A constant times an integral is, you can pull the constant out. And the radius, we already said, was y. And I have to square that, so that's y squared. And the thickness of each disk is very, very thin. It's that dx. So those infinitely thin disks. And I'm going to count all of those disks all the way from x equals 0 to x equals 2. And that's how I'll do the integral there. So the next row, I'm going to substitute the formula for y instead of just y. Because the formula for y was y equals x squared. So I'll put in an x squared every time I see a y. And there it is. So it's x squared squared, because it's the pi r squared. So it's x squared squared times dx. And that's basically x to the fourth. The integral of x to the fourth dx evaluated from 0 to 2. So what does that give me? It gives me x to the fifth over 5, evaluated from 0 to 2. And don't forget to multiply it by pi. So I'll just plug in a 2 for x and subtract plugging in a 0 for x in both situations. The final answer is 32 pi over 5 cubic units. So there it's a volume. And I've gone ahead and calculated the exact volume of that solid using integration. By the way, we usually leave pi alone. We don't bother to try and type in the long value of pi if you're doing this on paper. And usually the homework assignment will let you just leave the value pi in there without having to get all those decimal places. So another important engineering technology aspect that you'll be using, not only in mechatronics, but also in just motor design and whether you're operating any kind of moving object, and that is the center of mass. So the center of mass is kind of that thing that if you put your finger there would balance, if you would. And we sometimes call that the moment, if you will. So if I have some point O, some origin, then the moment is the mass multiplied by the distance from that origin. So that's meaning that if I had some object that had a whole bunch of different masses on it, I could find the center of mass by adding up all of those different moments, if you will. We'll use the moment later on when we go ahead and talk about things that spin. So let's imagine that we've got a plate of material, let's say aluminum, and we're cutting it in the shape shown in the graph here, this light blue color. And I want to find the center of mass of this plate because I want to be able to balance it and find out where the center of mass is. So the plate is defined by the formula y equals x squared, and it goes all the way from y equals 0 all the way to y equals 4. How can I find the center of mass of this object? Well, I have to look at it, and I realize that it's symmetrical on the y-axis. So I know that the centroid, or the center of mass, is going to be somewhere along that y-axis going up and down. But I don't know how far along the y-axis, because it's not going to be halfway. It's not going to be y equals 2, because it's definitely wider up at the top than it is at the bottom. So it'll definitely be heavier up top than it is at the bottom. So where is exactly that center of mass? I'm going to have to add up all of the masses of these infinitely thin rectangles. And in this case, instead of doing dx, I'm going to do dy, if you will. You see how the rectangles are kind of horizontal. I'm going to add up all of those slices, and then I'm going to divide it by the area, and that will tell me the centroid, or the center of mass. So the moment of that element, of some element, that little rectangle that I've picked, is equal to y, which is the distance from that origin O in figure 2640. The distance of that slice from the origin is O, and that's therefore y. I'm sorry, the distance from O is y. How far up on the thin plate it is, multiplied by 2x, which is how big that portion is. That 2x is that thickness. And we also need to know the height of the plate, and that's that infinitely thin dy. So the moment is on the numerator of that fraction. At the very top there, it's y times 2x dy. It's the distance from the origin multiplied by the size of the rectangle. And in the denominator, we have to take the just the size of the rectangle, just the area of that rectangle. And once again, the width of the rectangle is 2x, and the height of the rectangle is that infinitely thin dy. So altogether, if I could add up all of those slices, all of those moments, and all divided by all of those areas, I could get the centroid. I could find out what the center of mass is for this weird shape. So let's go ahead into the second line, the bottom line of the formula. I have to take y times 2x, and I remember that I can replace x with the square root of y, because remember, the original formula for the parabola was y equals x squared, so therefore x equals the square root of y. So I've gotten rid of the x's in the numerator and the denominator by replacing x with the square root of y. So in the numerator, in the next step, I see that I've got 2, I pull the constant out, 2 times y to the 3/2 power. I've combined a y times a y to the 1/2 power, and that makes y to the 3/2 power. And I divide that by the integral of 2 times y to the 1/2 power. That's the square root of y. Now, taking the indefinite integral, this is a definite integral because I know the two ranges of the integral from 0 to 4. I end up having 2 times, in the numerator, 2 times 2/5 y to the 5/2 power. And in the denominator, I have y of 2 times 2/3 y to the 3/2 power. And I evaluate both the numerator and the denominator at values 4, and then I subtract the value at 0. And I end up with 4/5 times 32 in the numerator and 4/3 times 8 in the denominator. I do some algebra and I find out that that comes out to 12/5. 12/5 is about, 2 2/5? We said it was going to be a little bit closer to the top than halfway. Halfway would have been a 2, and you can see here this is 2 2/5. A little bit closer to the top is the center of mass. So if I go ahead and measure 2 2/5 and I put a hole right there in the center of it, it'll balance perfectly well. So that's an engineering application of finding the centroid of a thin plate using integration. Now, once we know all these moments of where the mass is and multiplied by the distance from some center, I can find what we call the moment of inertia. Now, you know that a heavier object will take more force to go ahead and push it than a light object. Well, similarly, a heavier wheel will take more energy to spin it than a lighter wheel. So that is all because of the moment of inertia. Now, if I took the same weight of a wheel, but instead of it being 1 foot around, instead I was 30 feet around, a huge wheel, even though it weighs the same, it's still much harder to spin because the mass is all much farther away from the center of the spinning. We call that the moment of inertia. So the moment of inertia is really how much it resists kind of being moved or changing its direction. So imagine I had an axis of rotation, this little dashed line here, and I had 3 different masses. Mass number 1, mass number 2, and mass number 3, M1, M2, M3. And there were 3 distances from the center of that spinning rotation. Distance 1, distance 2, and distance 3. So we basically call the moment of inertia the sum of all of those individual moments. Moment 1, which is m1 d1 squared, it's the square of the distance. And then m2 d2 squared, etc., all the different masses added up. So that's why when they want big, heavy wheels that are hard to get spinning and hard to stop, they not only make them heavy all the way around at the edges, but they also make them very big so that they have a greater distance there. So another word that I want you to learn is the radius of gyration. So if I had all of these masses and they were all different distances and I'm spinning them around, the radius of gyration would be if I replaced all the individual masses with just one mass and spun it around at a certain radius, then how far would it have to be so that you couldn't tell the difference? So you could have all these different masses on a wheel spinning around, but you could replace them with a single mass, like imagine a rock attached to a string spinning around. It would be the same difficulty to start it up and stop it. So that's that moment of inertia. So let's find the moment of inertia and the radius of gyration for 3 masses. And they're all along the same line. That's that second graph there. The 3 blue dots, one is 3 grams and it's located at x equals -2. One is 5 grams and it's located at x equals 1. And one is 4 grams and it's located at x equals 4. So I want to spin this around the origin, which is at x equals 0. And let's say they're centimeters, where each one of those numbers is in centimeters. So we have grams and centimeters. So how would I find that moment of inertia? Well, we use the mass times the distance squared. So 3 times -2 squared plus 5 times 1 squared plus 4 times 4 squared. Basically, it's got 81 grams per centimeter squared of inertia. this whole thing. Now, what would be the radius if I took a single 81-gram weight instead of those 3 individual weights? How far away would I have to put it from the origin? What's that radius of gyration to get the equivalent spinning up and spinning down moment of inertia? Well, I would just take the individual masses and add them up and take that r squared, that radius of gyration, and that should equal the same moment of inertia. Well, we already know the moment of inertia is 81 grams per centimeter squared. We know the individual masses, m1, m2, and m3. And all I need to solve for is r squared, and that ends up being 81 over 12. Take the square root of that, I get 2.6 centimeters. So if I put an 81 gram weight 2.6 centimeters away there, that would have the, one single weight 2.6 centimeters away from there would still have the same 81 grams per centimeter squared moment of inertia. So that's just what the meaning of moment of inertia is. But of course, you know, since this is a chapter about integrals, we're going to want to find it for not individual masses, but instead we want to find moments of inertia for thin plates and solids. So let's start with the thin plate. Now we've got, let's say, a fan blade, propeller looking fan blade here in blue, and we want to spin it around the y-axis, and we want to know the moment of inertia, what it's going to take to get that up and spinning. So not counting wind resistance, we need to know the mass of that object and its moment of inertia. So really, I'm going to add up those infinitely thin rectangles that you see shown on top of the light blue area. And it's bound by the height of the rectangle is on the bottom, it's y1, which is some function of x, and on the top, it's y2, which is another function of x. We're not providing you the function here, we're just explaining how to do the math. So some curve y1 and another curve y2, and they define the top and bottom of each little rectangle slice. And we're going to add up all those slices from point A to point B. Once again, we're not given the exact values, we're just explaining how to do the problem. And the width of each rectangle is that infinitely thin dx. So we need to know the mass of whatever this plate is made of. So if it's plastic, then the letter K will be a light value, whereas if it was made of iron, then the letter K would be much heavier. And so K is the mass per unit area. So the area of the element is y2 minus y1, which is the height of the rectangle, multiplied by dx, which is the width of the rectangle. And the distance from the center of the axis where we're going to spin this propeller, which is the y-axis, the distance there is that dotted line x. So x squared times the area, all that multiplied by k, and I can pull the k out because it's a constant, all multiplied by k, which is the mass per unit area. So that's really how I would find the moment of inertia for some sort of irregularly shaped object that I could do the formulas for. If I wanted to find the radius of gyration with respect to the y-axis, I could first find that moment of inertia, that I sub y that I'm showing you above, and then divide that by the total mass of the plate and find the square root of that. That would give you the radius of gyration. We'll go one more level of trickiness. Here we've got a solid, and we want to know what its moment of inertia is if we spin the solid object. So we're going to take a solid object that's defined by a kind of a sideways parabola. It's actually not a parabola, it's y cubed, but it's y cubed equals x. And basically we're going to spin that function around the x-axis. And we're also going to take another straight line, y equals 2, and spin that around. And that'll form this solid, which essentially looks kind of like a shot glass on its side, if you will. And I'm going to have to take, instead of rectangles, I'm going to add up all the infinitely thin cylinders to find the total volume of this object that's in blue. So you can see here the dark blue is the area bounded by y equals 2 on the top and y cubed equals x on the bottom. And I spin that around the x-axis and I create this solid object that looks kind of like a shot glass on its side. So I want to go ahead and add up all of these locations times, let's say it's made of some solid material like, well, we'll go with glass since we're going with the shot glass analogy. Some glass material that has a certain weight, and we want to find the moment of inertia if we spin this on the x-axis. So we have to find the distance from that element to the x-axis, and in this case that distance is y cubed because y cubed equals x is the bounding of that distance. And then the area of it is x1 minus x2, how wide the rectangle is, multiplied by how tall that rectangle is. That's dy. And I want to spin that rectangle all the way around to form a cylinder, and that's where I've got the 2 pi. And the k represents the mass of glass, how heavy this glass is for that per unit area there. So I know the mass of glass per unit area, and I create all these rectangles spun around the x-axis into a cylinder, and then I add up all of these cylinders from 0, y equals 0, all the way to y equals 2. So this is just integration on its side, so we're going dy instead of dx, and we're having y change from 0 to 2. And we're going ahead and simplifying the integration by getting rid of the x's and replacing them with y's. We know that x2 is equal to x2 minus x1 is equal to y cubed. And when I take the integral of that, I've got y to the 6th, and I take the integral, that's 1/7 y to the 7th. That's the third row there. You can see 2 pi k equals 1/7 y to the 7th. And I want to evaluate at 2 and at 0 and subtract 1 from the other. So that leads me to have 256 pi k, and I leave the k and the pi alone. I don't bother to try to put them in there, all divided by 7. So that's the inertia, and the mass is basically k times whatever the total volume of glass used in that shot glass. So there I've got x times y is that basically that volume, if you will, and I'm going to integrate that from 0 to 2, and the total mass is going to be 2 pi times, and I replace y cubed for x once again, and that gives me 2 pi k 1 over 5 y to the 5th, and I evaluated at the value 2, and I subtract the evaluated at the value 1, I'm sorry, the value 0, and I get 64 pi k over 5. So if I were to want to find that radius of gyration, I could also take the square root, and I could find that radius of gyration as well. So we can find the moment of inertia, the total mass, and the radius of gyration of objects of irregular size. So that's about as complicated as these applications of integration get, but I did want you to have me walk through at least one of those. And you can see this example as well as a few others in the textbook, and on the homework there'll be 1 or 2 of these. Other applications that come up quite frequently in engineering technology is the total amount of work. So we always talked about work as being some sort of a constant force and multiplied by however far distance you push that. So if you have a 10-pound object and you push it 10 feet, you know, that's you did how many foot-pounds? You did 100 foot-pounds of work. But that's assuming that you're providing a constant force throughout the entire distance. What if you're not providing a constant force throughout the distance? What if the force is changing as you move through that work? The total work really then has to be this integral this sum of infinitely small little works that you're doing along the way. So let's take a look at an example so I can explain that. I've got this cable that I've got to lift to the top of a stadium. It's a 100-foot long cable, and it weighs about 40 pounds per foot. And I have to know how much work it's going to take for a motor to go ahead and move that cable. Remember, work is the total amount of work, and then power, which is many times what motors are rated at, is how fast you can do that work. So first I need to know how much work I need to do, and then I can buy the right horsepower or foot-pounds per second power to decide how fast I want to lift that cable to the top of, let's say it's a stadium or an arena, and getting set up for a show. So I want to wind that cable up. That's a pretty common thing to do in large auditoriums. And it's 100 feet long, and I want to wind it up 60 feet, so it's still hanging 40 feet off the ceiling. And it weighs 4 pounds per foot. What's the work that I'm doing there? Well, obviously the work that I'm doing varies. The more I wind up the cable, the less heavy it is and the easier it is to lift. So we're going to let X denote how much of the cable is still hanging down there. And therefore dx is that infinitely small little smidgen that we've lifted it. And the force required to raise the remaining cable is basically 100 minus x, 100 feet minus however much I've already lifted it, multiplied by the 4 pounds per foot. So the force required to lift the cable is 4 times 100 minus x. Since the 60 feet of cable need to be wound up, and to begin with, none of it is wound up. It's all starting at 0. And by the time we're done, 60 feet of it will be wound up. So the work done is going to be the integral of that original formula, 4 times 100 minus x times dx, that little infinitely small distance that we do the work, evaluated as an integral from 0 to 60 feet. So I go ahead and take the integral of 400 minus 4x, and multiply the 4 in there, and I get 400x minus 200x squared. And I'm going to want to evaluate that at 60 and then subtract that from it evaluated at 0. So at 0, the value is 0, so that was easy. All I have to do is plug in, what is it, at 60? It's 16,800 foot-pounds of work that were done to go ahead and lift that cable. That's a lot. That's the same thing as raising 16,000 pounds 1 foot. I mean, that's still a lot of work that was done. And you can see that you're going to need a strong motor if you want to do that fairly quickly. Otherwise, you're going to have to do it pretty darn slow, because that's quite a bit of work to lift such a cable. So when you're done with the homework, you're going to have a quiz covering all of Unit 3. So all 18 questions in that quiz are going to come from the chapter, basically covering the topics that we just covered, that are in the chapter, and that you're doing in the homework. Also, the final exam is going to have about a half a dozen questions right from this chapter. So things like finding the voltage as it changes over time, finding the area between two curves, finding the volume of a solid that might have been rotated around an axis, finding the center of mass, and then finding the work done, or the average values of functions that vary. So those are the kinds of things that you need to focus on, basically what it is we just covered for the assessments that are coming up. You'll notice that the study sheets that are provided cover the following terms that are all in Chapter 26. You really need to understand what's the meaning of area under the curve, solid of revolution, disks, elements of volumes, moments, center of mass, moment of inertia. What is the meaning of work? So obviously those are definitions, and the study sheet kind of covers them and has a few formulas relating to them as they relate to Chapter 26. So thank you so much for taking the time to listen to this lecture, and I hope it's helped you in your homework for Unit 3. It's the only homework that we have in Unit 3 because Chapter 26 is a fairly important chapter that we need to cover. Thank you so much. My name is Paul Nussbaum, and I appreciate your time.